Welcome back everyone. Today we are not just writing code, we are becoming memory architect. Before we build a linked list, we have to understand why we need one. We usually start with arrays. Arrays are great, but they have a fixed reality. They are rigid containers. Imagine you create an array of size 5. It demands a continuous block of memory. But what happens when you need to add a sixth item? You hit a wall. You can't just tape a new slot onto the end. To grow an array, you have to perform an big O N operation. You have to find a bigger space and literally copy every single item over to the new location. The entire array must be copied to expand. This is the cost of resizing. It is expensive and efficient for dynamic data. Enter the linked list. Data structures are not just containers, they are solutions to architectural constraints. The linked list solves the rigidity problem using non-continuous memory. Think of it like a treasure hunt. Data is not stored in nice, neat indexes like 0, 1, 2. Data is stored in nodes at random addresses in memory. The crucial part: each node holds a map reference, a pointer to the next one. You don't need a continuous block of space, you just need to know where the next clue is. Let's look at the anatomy of a node. It has two parts: the value, your data, and next the pointer. In code it looks like this: private class node, private int value, private node next. However, there is a limitation I call the one-sided love. Node A knows exactly where node B lives, but what about node B? It has no idea node A exists. Traversal is strictly unidirectional. You can only move forward. To control this chaos, we need anchors, the head and the tail. The head is our entry point. If you lose the head, the garbage collector eats your list and it's gone forever. Now a pro tip for architecture: always maintain a tail pointer. Why? Without a tail, if you want to insert an item at the end, you have to traverse from the head all the way to the last node. That is an big O and complexity. With a tail, you can jump directly to the end to link a new item. That makes insertion big O1 instant. It is a massive optimization. The golden rule of linked list is this: visualize pointer changes before coding. If you write code blindly and lose the reference to the next node, the chain is broken forever. Let's visualize inserting at the head in 3 steps. First, create a new node appears, let's say with value 14. Second is link. Draw an arrow from the new node pointing to the current head, that is node 3. Third is update. Only after linking do we move the head tag to point to our new node, that is 14. Now look at how the code maps directly to that visual. Here, notice line 2, node.next equal to head. We secure the connection before we reassign the variable head. If you swapped these lines, you would lose the whole list. What if we want to insert somewhere in the middle, say at index 3? You never move the actual head pointer to traverse. If you move head, you lose the start of your list. Instead, we use a disposable temp variable. Think of temp as a temporary copy of the map. We use temp to travel to index -1. We say temp equal to temp.next to hop from node to node until we reach the insertion point. Here is the structural flaw of singly linked list, that is deletion complexity. Deleting the first item, easy, big O1, just move head forward. Deleting the last item, that is tail, that is the bottleneck, it is big O-N. Why? Because even though we have a tail pointer, we can't look back. To delete the tail, we need to tell the second to last node to point to null. But we are standing at the tail and we have no way to reach the node behind us. We are forced to traverse the entire chain from the start just to find that second to last node. This leads us to our next evolution. To fix the looking back problem, we upgrade to the doubly linked list. The node gets an upgrade. Now you can see in the code there is a node previous. This is the upgrade. This gives us bidirectional navigation. We can go forward and backward. However, this power comes with responsibility. Inserting into a doubly linked list is what I call the 4-pointer dance. You have to wire 4 connections. New node dot next points to B, new node dot previous points to A, B dot previous points to new node, and A dot next points to new node. Warning here, beware the null trap. Always check if node dot next not equal to null. before setting a backward link. If you try to set .previous on a null neighbor, you will get a null pointer exception. Next evolution, the circular linked list. Here the tail.next point right back to the head. It creates an infinite loop. This is used in things like music playlist, repeat all or round robin scheduling for CPU tasks. Traversing this is tricky. If you use a standard while node not equal to null loop, it will run forever because null never exists. The solution is the do while loop. This guarantees the code runs at least once and stops only when we arrive back at the start. So which should you choose? Let's look at the stats. Accessing an index, arrays are king, big O1. Linked lists are slow, big O-N. If you are insertion at the start, linked lists are king, big O1. Arrays struggle, big O-N. Rule of thumb, use arrays for fast retrieval like reading data. Use linked list for dynamic modification, adding, removing data constantly. To truly master this, you will want to explain patterns like fast and slow pointers for detecting cycles and recursion for solving problems like reversing a list. Remember, do not just memorize the code, memorize the visual movement of the pointers. If you can draw it, you can code it. Thanks for watching. Now go grab a piece of paper, draw some boxes and arrows, and build your own linked list.